Find extremal for the functional integral 0 to pi y dash square minus y square plus 4y cos x dx provided the boundary conditions y of 0 equals 0 and y of pi equals 0. We have capital F is the function y dash square minus y square plus 4y cos x. We have fy equals negative 2y plus 4 cos x, treating y dash and x as constants. We have fy dash equals 2y dash, treating y and x as constants. When you give these expressions of fy and fy dash in the Euler's equation, you get the equation negative 2y plus 4 cos x minus 2y double dash equals 0. Dividing both sides of this equation by 2, you get the equation negative y plus 2 cos x minus y double dash equals 0, which can also be written as y double dash plus y equals 2 times cos x. We have the differential equation of second order obtained as d square plus 1 applied on y equals 2 times cos x. We have the auxiliary equation by just replacing the operator d by m, and we get auxiliary equation m square plus 1 equals 0, which gives the roots m equals plus minus iota. We have the complementary function obtained as y equals c1 cos x plus c2 sin x. In order to find out particular integral, we have to evaluate 1 by d square plus 1 on RHS 2 times cos x. 2 is a constant and it can be taken outside the operation of operator 1 by d square plus 1. So we have particular integral equals 2 times 1 by d square plus 1 applied on cos x. Whenever you have 1 by f of d square acts on cos ax or sin ax, you have to replace d square by negative of a square, where a is the coefficient of x in the expression of cos ax. This is valid whenever f of negative of a square is not equal 0. Here we have cos ax has a equals 1, because the coefficient of x in the expression of cos x is 1. Therefore, we will replace d square by negative of 1 square. Thus, d square is replaced by negative 1 and we obtain the denominator as 0. Since the denominator became 0, we have to take the derivative of operator f of d, and thus the particular integral becomes x into 1 by 2d applied on cos x, because 2d is the derivative of d square plus 1. 1 by d is inverse differential operator, or we can perform integration over cos x. We have integral cos x equals sin x. Thus particular integral is obtained as x by 2 into sin x. When we were evaluating particular integral, we already had a constant 2 which was taken outside the operation of 1 by f of d. So we can cancel 2 and 2, and thus we have particular integral obtained as x sin x. It remains to apply boundary conditions on the expression of complementary function. We have the boundary conditions y of 0 equals y of pi equals 0. And our complementary function was y equals c1 cos x plus c2 sin x. Applying the boundary condition, we obtain 0 equals c1 cos 0 plus c2 sin 0. We have sin 0 equals 0 and cos 0 equals 1, from where we have c1 equals 0 obtained. Now, when you give the second boundary condition y of pi equals 0, in this expression you get 0 equals c1 cos pi plus c2 sin pi. c1 has already determined as having value c1 equals 0. Since sin pi is also 0, from this equation we are getting 0 equals 0. Thus, c2 is found to be a free variable. Infinitely many values are possible for c2. Even then, this equation remains satisfied. This is a case of existence of infinitely many solutions. Applying the boundary conditions, we obtained the conclusion that c1 equals 0 and c2 is a free variable. When you give these observations in the complete solution expression, we have complete solution equals complementary function plus particular integral, which is c2 sin x plus x sin x, where c2 is a free variable, which can also be written as c2 plus x multiplied to sin x, and this is the required extremal.